Funktioniert? Ja. Okay, yeah, thanks for the introduction, Klaus. So my name is Jörn Huber. I'm also a postdoc in Matthias' group. I worked a lot in the field of image reconstruction and sequence programming, mainly on topics related to motion correction and anterior spin labeling during my PhD thesis. Yeah, and right now I'm mainly involved in software engineering tasks and some principal research on MRI. Yesterday and today we already saw many different MRI techniques, for example the SPAM technique which Mareike introduced to us. We saw some T1 and T2 weighted imaging from Matthias' teaching tool yesterday. We also saw how to suppress specific signals from, for example, fluids or fat using inversion recovery sequences. And we also heard about anterior spin labeling. And of course, all of these techniques somewhat rely on images which are free of artifacts. But usually that's not that easy to achieve in clinical practice, to get perfectly free artifact or images which are perfectly free from artifacts. So as we are playing around with some clinical protocol parameters in the afternoon, in the session after this talk, where you will definitely encounter some artifacts, it might make sense to discuss some of those artifacts in a bit of interactive way. So I'm going to show you some artifacts, and maybe some people already know them and could comment on them, what they are, and then we can have a quick discussion on them. So yeah, as I said, in principle, you want to achieve images like this, so perfect brain images, perfect abdominal images, which you can then use to, for example, to directly derive information from them or to use them to process them with quantitative tools. But as I said, usually you won't achieve that. And one of the most common artifacts that you could produce at MRI systems is something like that. So you see the object which is somewhat extended over your field of view and arrives at the other side again. So did anyone maybe produce some artifacts like that at the MRI system and knows what's going on there? Or anyone knows how it's called? Yeah?
Is it related to the field of view and being very small?
Yeah, so that's the main reason, so that your field of view is too small. So do you know how they are usually referred to, or how they are called, these type of artifacts?
I think because we are dealing with frequencies, this is aliasing.
Yeah, that's perfectly right. So you usually call them aliasing artifacts or wraparound artifacts, and the reason is, as you said, so the field of view is too small for the object which we want to image. And why they are occurring is actually quite easy to understand if you just look at the math which is going on during an MRI scan, or basically during the encoding of your system. So this is basically a one-dimensional Fourier transform. So you have your signal S, which is the k-space. Then you have like the image, which is this X, which is dependent on the position in image space. So basically the magnitude of your signal, or the complex signal. And this is basically by your imaging gradients from the MR system, you apply specific phase increments on your spin ensembles at specific positions in your field of view. And if you then look at such a field of view where we have some sort of an object in there, you basically could apply these different positions based on the field of view. So for those areas at the boundaries of your field of view, you will always have the position n divided by 2, or minus n divided by 2, and n divided by 2 minus 1. And based on the formula for the Fourier transform, you could actually analyze what happens to your spins in the transverse plane due to the gradients which you apply at a specific position. So for example, you could consider such a spin ensemble at a position which in this case is n divided by 4, because it's the half way between the center and the outer edge. And from this position, you could actually calculate how the phase increment of this spin should look like from this exponential term. And if you do that, you basically see that this spin with each step in k-space should acquire pi divided by 2 of phase. So that means if you now step through k-space, you would basically increment the phase of that spin by pi divided by 2 with each step that you go through k-space. And this is basically what happens to every other spin in that field of view. Dependent on their location, you could calculate this, and with each step that happens. So now you could consider what happens if you have a field of view which is too small. So as I said, you would basically have your field of view, your object tends over the edges of the field of view. That means you have basically parts of the object which are not encoded inside the field of view, and you have your linear gradient which should somewhat encode the object. So you could again calculate how these phase factors should look like. So at the edges you would have like minus pi and pi, which are for the increment with each step in k-space that you acquire. And for those spins which are outside the field of view, you basically, you are at pi, you would just go one farther around. And then you again get a phase increment of pi divided by 2 for this one, and minus pi divided by 2 for the one on the other side. And if you then look at the phase information that those spins would have after one encoding step, you directly see, okay, those spins would have the same phase. So this one would have the same as this one, and this one would have the same as this one. So what that means is, if you then encode your signal and acquire everything with your coils, it appears as if those spins are basically at those origins, because you simply have the option to encode between minus pi and pi. And that's exactly the reason why you get those wraparound or aliasing artifacts in that case. And actually that happens every time. But usually, so if you would have your gradient, you would always encode additional phases on spins which are outside the field of view. But if you're clever, your object is only inside the field of view, so those will not give you any problem for your final imaging. So that is why you should always keep your field of view at least to the edges of the object that you want to measure. And one thing to basically solve this problem, if you want to have a field of view which is smaller than your object, is so-called oversampling. So what you could do is, if you have, basically the field of view is related to the step size in k-space, how you traverse through it. And you could simply double that for example, the readout direction, which will double the field of view, and then you get rid of the problem with these aliasing artifacts. And this is actually what is usually done by all of the all of the systems would apply on a daily basis for the readout direction, because as this is the frequency encoding direction, you can just sample at the double the bandwidth, and then cut off the not needed parts of the field of view in the end. So you usually do that. That's why you won't get aliasing artifacts in the readout direction at clinical systems. But you would still get artifacts, for example, in this phase encoded direction. This is usually due to the case that phase encoding is more expensive in terms of measurement times, because if you have a sequence which acquires line by line in the phase encoded direction, or you would just need to apply additional phase encoding steps, and this is not very time efficient. So it's not that common to do that. But for the readout oversampling, it's usually what you would do actually in clinical scans, and which is automatically done at most of the systems. So the next artifact is this one, or does anyone know what is going on in that image? Has everyone seen something like that before? I think Lucas saw that quite often already. Yeah, and do you know some type of sequences where such ghosting usually occurs, or occasions where it occurs? Yeah, so you usually see something if there's motion during the scan, but we also see something like that, for example, in if you use EPI sequences where we don't correct for that. And I mean, this is still quite usable, I think, but you also get images like that where it's where you have like ghosting in abdominal regions, which is also overlaid with other artifacts like chemical shift and geometric distortion. So it's not that easy to distinguish between the different types of artifacts. So you usually want to get rid of that. And again, you could analyze a bit of math to identify why that is happening. So usually what you have is like you measure K-space with your MRI sequence. And this K-space, if you would apply a Fourier transform, you could, or you would get your complex image space. And this is basically consists of a magnitude image. This is what we usually look at MRI systems, and a phase image, which encodes the image phase. So if you want to understand how ghosting occurs at systems, what you would need to do is to split that up into two different data sets. So you could just say, okay, this is the sum of even and odd K-space lines, and mathematically you could formulate that as basically the full K-space set multiplied with a so-called comp function. So it's just that you say, okay, we have 1 and 0, and if you multiply that, then you would get rid of all the odd lines in that case and all the even lines in that case. And if you do something like that, as the Fourier transform is basically linear, you could just say, okay, I apply the Fourier transform to this data set, and I apply the Fourier transform to this data set, and if I add both images together, the result should be the same as before. And if you do that, you will see something like this. So you will notice that you, in the magnitude images, will get these ghosting artifacts that we saw before. But what you also would notice is that for the phase information, you basically get the real image which you want to have, which has a flat phase, and you get the ghosting signal, which has opposite directions of the phase. So this is basically related to some Fourier theorems. But the important thing is, if those are directly opposite, or the phase information of those ghosts is directly opposite, you could just sum them up in image space again, and they would cancel out. And this is why if you have the combined set of K-space lines, you would not see the ghosting. And based on this analysis, you can quite easily understand why you would see ghosting in different situations during MRI scans. So for example, you could consider this situation. So you would have different amounts of signal available when you measure partitions of K-space. So usually you would, for long scans, or if you want to acquire many partitions or lines, you would split your set of K-space data up into multiple segments. So you would not acquire all of the segments after a single excitation to be a bit more efficient when, on the signal side. But you have to be careful with the available signals. So if you apply, measure the first segment, like this one above, so the even lines, with the equilibrium magnetization available, you have a lot of signal, which translates to quite a lot of, or quite some high intensity of those K-space lines. And as this is just a multiplication, this will also translate to quite high intensity of your image magnitude which you get there. So if you directly acquire another image after that, you will have less magnetization available. So that means that you will get an image or the image magnitude which is a bit lower than what it was above. And if you now would just add up those two, you will just see, okay, the phase stays the same, so it should cancel, but the magnitude is not the same. So you will result in an image which has ghosting, and which you will definitely, or which you can produce with the gammaSTAR framework, which we will see after this session, and which you usually see at clinical or at your MRI system if you don't wait long enough after your first excitation to acquire the next K-space segment, or you would apply some preparing scans such that if you acquire the first segment, you don't have the full magnetization available, but you are already in this so-called steady state where you only have a tiny fraction of magnetization, but the tiny fraction is the same for both segments, and then everything would cancel out again. And you could also directly see from this K-space data set that there is some intensity fluctuation between even and odd lines, and this is why you get the ghosting in that in those images basically. And the next thing which you could analyze is basically EPI. So we already said that this is a quite usual case where you see image or where you will see those ghosting artifacts. So there the situation is a bit different. Of course, you could also, if you segment it, you could also end up with different image intensities or signal intensities, which will add up to the effect which we see here. But in principle, the problem with EPI is that you acquire k-space lines in an up and down fashion with this zigzag trajectory. And as there are some gradient delays and stuff like that, you will have a tiny shift between when you acquire the line in an up fashion. The center will be a bit shifted upwards, and if you acquire the downways, you will shift the center a bit downwards. And basically, shifts in k-space would translate in linear phase modulations in image space. So what you get here is this situation. So now from the magnitude images, those look quite similar. But if you look at the phase images, you see that there's a linear variation of the phase of those ghosts. And this linear variation is not the same for this even ghost and this odd ghost. So if you add both together, you will get some quite strange modulation of your ghost images and of the main image too, because that also has this phase modulation. And you will see like these shifted lines in k-space for your k-space data set. So this is typically what you see with EPI sequences, and this afternoon we will also learn how they are usually corrected. Yeah. So the next artifact would be something like that. So anyone already noticed that? So for example, if we compare those with those, so what is going on there? Anyone saw something like that before? Or in the upper row, if we acquire an image with a high bandwidth and with a low bandwidth, and it looks a bit squeezed. So someone already saw something like that. So basically that's called geometric distortion. I also mentioned that before for this abdominal image which we saw. So this is quite typical for all kind of EPI-based sequences, and that's also the case for something like 2D grays or 3D grays, which you usually use for geospin labeling measurements. And the basic reason is, in principle, that your main magnetic field during MRI examinations is not constant. So with this formula of the Fourier transform, you basically assume that, or what is behind that is that your gradient is perfectly linear, and this is related to a perfect homogeneous magnetic field of 3 Tesla or 1.5 Tesla or something like that. But in reality, what you will see is something like that. So you put a brain or some kind of object into your scanner, and this will always change locally introduce some changes to your main magnetic field. And the reason is that a brain, for example, has some paramagnetic properties which will increase or change the local magnetic field depending on the type of tissue or some type of boundaries between tissues that you have in some regions of the object, which will then result, for example, in some deviations which are quite high or quite fast, so they are changing rapidly, and there's also some slower changes in the magnetic field strength over some larger areas of the object. And this is a problem, and we could basically also quite easily understand why this results in these geometric distortions that we saw before by analyzing again what your gradient should do. So in principle, you would have your gradient, and we saw before that this gradient basically introduces phase shifts depending on the position of the spins. So you would, in this case, consider that you now have an additional small portion of field inhomogeneity. And what now happens is that all of your spin ensembles would collect the phase based on their positions due to the gradient. And after the gradient is switched off, your spin ensemble, which is at this inhomogeneity, would also collect additional phase until the next gradient would be applied. And if we look at that, again, we have the situation that this is not distinguishable from that. So it appears that all signal which would be located here is shifted to there, and this is why you get those geometric distortions. So what happens is that in your final reconstructed image, all signal from there appears to be shifted to the right. Did anyone ever work with some kind of techniques to correct for something like that? Maybe the arterial spin labeling people know something, what you could do. Yeah, so what you usually do is to acquire two sets of images. So with API, you could acquire one image, for example, in this case, which has the phase encoded direction in this direction. So everything is shifted upwards for those inhomogeneity parts. And in the other case, you would acquire the same image, but change the phase encoded direction to downwards. So everything is shifted to the downwards to this part. And by doing this, you basically can calculate an undistorted image where you can then perfectly reconstruct how the actual distribution of signal should look like and how this inhomogeneity map should also look like. And this is quite often used for EPI sequences and for, basically when we do post-processing on arterial spin labeling images too, because they are based on this 3D Grace readout, which has the same problem basically because it relies on an internal API readout. So a special artifact which is somewhat related to that is this. Anyone knows what's going on there or has an idea? Yeah?
Maybe it has to do with the air tissue interface, but I'm not sure.
Yeah.
I see that it's close to the sinus.
Yeah, so it's basically, so the air tissue interfaces are usually a problem which will introduce like these geometric distortions before, because as you said, usually in those areas you will have like these really high local deviations from the main magnetic field. In this case, it's even worse. So this is basically some type of susceptibility artifact. So there you would usually have some sort of metal inside your system, which will really introduce a large change of the main magnetic field. And in that case, you will get, depending on your type of sequence, a really strong geometric distortion, as you see it in here. So there we also have a combination of like geometric distortion and this wraparound artifact, because they acquire such a great or large amount of additional phase. And here, for example, you have some sort of gradient echo-based sequence where this artifact basically results, or where this deviation from the main magnetic field results in a quite rapid loss of the spin coherence, so you won't measure any signal at all at that position. And what you could also see is something like that. So anyone could imagine what was going on there? Yeah, so basically that's an artifact from this type of hair gel. So it contains some, or it appears that hair gel might contain some ferromagnetic particles. So if you have a subject in your scanner which has a lot of that, so I assume that it's not the case for all type of hair gels, but there are at least some where that is the case. Yeah, and then you might end up with something like that. So you really have a distribution depending on the type of hairstyle that the person has, where you have large areas of ferromagnetic particles, and they will really introduce large fluctuations in your main magnetic field. So you really get, just not really usable for diagnostics, maybe, but I'm not a clinician. No, I don't think so. Not that, but yeah, probably the person need to wash the hair before the scan was repeated or something. Something which is a bit related to those type of artifacts is what we see here. So this is an image of the brain. So we see some shifted signal which appears to be here, but which should not be there. And this is a an ugly image from my dissertation from the liver, actually. And there you also see this large band of signal in the central part, which should not be there. So anyone knows what's going on there? So it's basically related to quite similar property, and I would assume that many of you already saw something like that. So those are basically chemical shift artifacts, which are basically a quite special type of off-resonance artifact or geometric distortion. So the thing is that your body does not only contain water protons, but they also contain that also contains protons, which are bounded in some lipids, and those will have those will experience a slightly different magnetic field than the water protons. So usually your whole system is tuned to the water protons, as this is usually what you want to measure, and this makes up the largest part of protons in your body, basically. But you also have those lipid protons, and they usually have a quite bright signal and fast relaxation time. So you should usually have them somehow in your images. And so the main reason or the main problem with that is due to this deviation from the actual water resonance. Those lipid protons would always acquire additional phase, as we saw quite often during this talk already. And this results in, again, some position shifts of that fat. So that means this fat would usually be somewhere like here, but the whole fat signal is shifted upwards and appears to be like here, and it overlays some structures which you might want to see, but which you can't see due to this artifact. And I think yesterday many of you also already learned about one way to suppress that. So you played around with, or many of you played around with T1 recovery sequences. So what you could do is, as fat usually has a quite low T1 value, which is quite different from like the gray matter and white matter values, which you usually want to see. What you could do is to apply a T1 or an inversion pulse, and basically tune your image readout to the time point where the fat signal crosses the 0 line. So there is no longitudinal signal from fat which you could excite. So if you acquire an image here, you probably won't see much fat signal in there unless you are doing ASL imaging, where you suppress everything, so you would see it nonetheless, and you really need to be quite good in your suppression techniques. But what you could also do, if that's not enough, is to do a spectral fat suppression. So there you would use another pulse, which is which has a special design. So it would excite only the lipid protons, but not the water protons. And if you then dephase them and acquire your actual image, you won't see the fat image anymore. And what you could also do is some model-based reconstruction, so basically somewhat related to what we saw with this top-up approach. So this is something that we developed for usage with ASL imaging. So there we see like this shifted fat signal, which we don't want to have in our images. So what you could do is to just, instead of using just a Fourier transform, you could develop a more complex model which includes this shifted fat, and then just do an optimization or conjugate gradient optimization, where you could then basically split all these types of effects which result in your distorted signal and shifted signal. So you would get control and label water images, you would get the fat images for them. You would also get an estimate of your B0 or your inhomogeneity map, and also this perfusion-weighted ASL signal in that case. So one thing that is also quite common are motion artifacts. So I think, basically this is the most common artifact, so to say, which you would encounter in your in clinical MRI scans. So it's quite obvious. So as we rely on usually we want to use our gradients, which encode the phase of spins based on their position. So if our object moves during the scan, this relation does not hold anymore, which will result in artifacts as we see it there. And the thing is that this occurs not only sometimes, but basically in almost all type of MR sequence that you're using. So there was a small study where they analyzed scans in a clinical setup, and they found that in almost 60% of scans there were at least some minimal motion artifacts during the scan. So this is basically the most common thing that will occur during routine imaging. And it's also quite clear because usually it's quite hard to really keep your head or whatever straight for more than 30 minutes or something. You will always have some minor motion during the scan, which could result in some problems. So what you could do is, to avoid that, you could apply some triggering or some fixation of the subject, or some time breathing during the scan. Or what you could also apply is basically some type of motion correction. So this is something that Daniel developed during his PhD thesis. So it's called prospective motion correction. The idea is if your subject moves during the scan, you would not just use, or you would not just want to correct that afterwards, but you could also acquire an image during the scan, analyze the position of the object, detect that it's some shifted upwards, for example. And after that, you could correct that by adjusting your imaging planes so it appears that the object remains still during the scan, although there was motion. So this is called prospective motion correction, which you would, where you would correct your imaging gradients and stuff during the scan. And if you do that nicely, you can just follow your subject, and you see that you don't have any motion artifacts anymore, in principle. And what you could also do is, for example, apply elastic registration. So there you would just sample images like the sagittal image of the liver. And after that, you would apply some motion correction techniques where you just apply a registration to make those objects match each other. And what is clinically used, or at least what is available on each major system, is the so-called Propeller technique. There you have a special type of readout trajectory of your case-based data, so you don't want to acquire case-based data in a Cartesian way, but there you have these so-called blades where you just acquire case-based with these blade-shaped segments. You could then, as each of these segments samples the central part, you could reconstruct a low-resolution image from that, do a registration, optimize the blade angle and phase in case space, as we see here. So some blades would need to be shifted upwards because the subject did a rotation during the scan. If you then apply the Fourier transform, you would end up with an image which is also almost artifact-free, and this is what is basically integrated into each MRI system of every major vendor. So the last artifact that I want to show is this one. So this is the final question to succeed in this exam. So if anyone can tell me what happened there, then that would be really cool. Yeah, it's related to motion. Yes, that's the patient leaving the scanner during the measurement artifact. So that was a subject which was, I think it was confused or so, or I mean, maybe some dementia related problem. So yeah, the person really left the scanner during the scans. So of course, nothing really useful was measured there. All right, yeah, so that's basically it. So the last thing I want to mention is again related to this hair gel thing which we saw before, to basically maybe introduce a somewhat better understanding of artifacts which we usually have. So usually we consider artifacts as something which is a problem, and we want to correct for that, or we need to get rid for that. But basically artifacts also tell you quite a lot about the object or subject inside your scanner. So for example, in this case, this tells you that this is somewhat the brain image, and you have this hair gel applied. And we also saw examples from Mareike, for example, with the spam technique, where you use stimulated echoes, which in some contexts would be considered as artifacts because they would introduce like this squared pattern in your image. But in some other contexts, they are quite useful depending on what you want to do. So usually, if you have an image artifact, that just means that your basic Fourier transform operation is maybe not enough to reconstruct the image. But if you would have a better reconstruction approach, you could probably extract additional information, for example, this hair gel information from the image, which could tell you something about the object which you would not get if the artifact would not be there. So usually, or basically, it's not that bad if they are there, but we need to be careful, if we can maybe exploit them or if we need to correct them because we don't want to have them. But it depends a bit on the application. All right, so that's it from my side. Any additional questions? So I think then, I don't know. So we have a 10-minute break, and I think after that we will proceed with a hands-on session where we play a bit around with MRI protocols, and maybe you can generate these different artifacts using the gammaSTAR framework, which you will be using after the break.